This is a review of a portion of the fundamentals exam for engineering registration. The topic for today's lecture is dynamics. My name is Ray James, Texas A&M University. My phone number is 409-845-2475, and you can reach me by email at r-james@tamu.edu if you have questions. As a resource for your study of this, your review of this subject, you have, I believe, a copy of the EIT Review Manual by Michael Lindberg, this document, which I will be following to some extent. And also I'll be referring to the handbook that's provided by the National Council of Examiners for Engineering and Surveying, the Fundamentals of Engineering, Discipline-Specific Reference Handbook. Now, there's a copy provided. My copy is marked review copy only, do not take to examination. My understanding is you can obtain one for your review and study. When you go to the examination, they'll issue you another one that doesn't have any pencil notes in it for your use in the exam. That'll be identical otherwise to the one you've got. So I'll refer to it from time to time too. I've tried to prepare the review in such a way that that's the only reference that's needed. It's my understanding that the examination is structured so that that's the only reference that is expected that they'll expect you to need. But there is some material in my presentation that's not in that exam, because the objective is to try to help you review your understanding and hopefully come to a better understanding of engineering mechanics and specifically dynamics. I want to be sure that I'm talking to the right audience. My understanding is the audience is individuals with an engineering degree or related degree, although perhaps not recent, so that your recent experience may not be engineering. The review will be fundamental because of this. It's hard for me to look into your eyes, as this is a taped lecture, and determine whether or not I'm lecturing above or below the understanding of the audience. So I'll ask your forgiveness in advance if I cover the material in too basic or perhaps to an advanced method. I didn't read this. I want to emphasize that engineering mechanics in general is the study of forces and motions. Specifically in statics, which is one of the traditional engineering mechanics courses, there are no motions, or at least there's no acceleration. In dynamics, we're interested in the study of forces and motions, usually on, and especially in this review, particles and rigid bodies. And in mechanics of materials, we apply this engineering science of mechanics to deformable bodies. Dynamics is traditionally broken up, for convenience of study, into two subjects. Kinematics, which is the geometry of motion, so you don't have to discuss forces while you're discussing kinematics, and then kinetics, which is really the general term for dynamics. We'll talk about three tools or three methods that are used to study dynamics problems. Newton's second law, which says in vector form here, the summation of the forces that act on a body, on a free body, is equal to the mass of the free body times the acceleration of the mass center, or of just the particle if it's a particle. The angular form of the equation of motion is not written here, but of course it's implied. And then we will use work and energy methods and impulse and momentum methods as appropriate to handle different kinds of two-dimensional particle and rigid body dynamics problems. we're going to be limiting our study, our review, to particles and systems of particles and to rigid bodies. With respect to kinematics, remember kinematics is the geometry of motion. We'll discuss kinematics of a special case of motion, rectilinear motion, which means motion of a particle in a straight line. This is the simplest case. If you define the position of a particle as it moves along some arbitrary straight line with a vector r, the magnitude of the vector r, of course, is just the distance from some reference that you define to the particle in question, then it follows that the velocity of the particle is the time derivative of the position vector, and the acceleration of the particle is the time derivative of the velocity vector, which is the same as the second time derivative of the position vector. And if we introduce a unit vector called I here in the direction of the line, so that I is, back on page 5, a vector of magnitude 1, no units, that is always aligned with the with an axis along the line of motion of the particle, then the position vector is r is some magnitude r, which is just the position of the particle, times the unit vector. Because the unit vector is a constant in magnitude and direction, and it seems trivial in this case, but it's important in later coordinate systems to see what's happening, the time derivative of the position vector is just the time derivative of the magnitude of the position vector times this same unit vector. So we write dr dt is equal to r dot, which is shorthand notation for time derivative of r, times the unit vector I. Similarly, the time derivative of the velocity vector, and that's what dr dt is the velocity vector, the time derivative of the velocity vector is derivative with respect to time of r dot in the I direction, and this term, r dot times time derivative of I, is 0. And we talked about why the time derivative of I is 0. It's always in the same direction, it's always the same magnitude, therefore nothing changes in I with time. Not all unit vectors obey that equation, so we have to be careful when we look at other coordinate systems, and this gives rise to different terms in the equations of kinematics. So we have, to summarize, for rectilinear motion, the position vector is some magnitude r of t in the I direction. The velocity vector is the time derivative of that r of t in the I direction, and the acceleration is the second time derivative of r of t in the I direction. Obviously, inverse integral relationships exist. If I happen to know the velocity, the speed, we call this magnitude the speed, if I know the speed as a function of time, and I can integrate that, and I know an initial condition on position, I can find r of t. If I know the acceleration, okay, as a function of time, and I have appropriate initial conditions on velocity and speed, velocity and position, I can integrate r once to get velocity and twice to get position. And that's what we mean by kinematics. Remember, we have to have those initial conditions, and I guess we sometimes don't write them specifically, but when we write the velocity of time is equal to a of t dt, a couple of things ought to be pointed out. A mathematician might cringe when we write it like that, because, and I'll try to be more careful in the future, because t here is a dummy variable that is going to range, and this t is the variable that we're trying to find the speed at, but this t varies from it can be anything. In particular, it's going to go from 0 to this particular time. So to be more precise mathematically, we'd want to write this as a dummy variable, say tau, and we'd want to take into consideration there's an initial condition. But you see this written like this in your handbook, and I wanted to call your attention to the details. We'll see how they're applied. Okay, so much for the simplest kind of motion, which is rectilinear. Let's talk about a more interesting motion, curvilinear. And of course, curvilinear motion, a special case of which is rectangular motion, rectilinear motion. Curvilinear motion we can describe using different coordinate systems. The Cartesian or rectangular coordinate system is perhaps the most common and most important, but in some problems it is very advantageous to the analyst to use path coordinates, normal and tangential, or cylindrical, sometimes called polar and two-dimensional, sometimes called radial and transverse coordinates. I'm going to try to walk you through the relationship between the position vector and the velocity and acceleration vectors as expressed in first rectangular and then path coordinates and then cylindrical coordinates or polar coordinates. First of all, in Cartesian coordinates, we have a coordinate system x, y, and z. Notice I always define the coordinate systems such that they're right-handed. If you wrap your hand around the z-axis, for example, with the fingers of the right hand, anybody that's left-handed here is going to be disadvantaged, but use your right hand, you rotate your fingers in the direction from x to y, your thumb points in the direction of the positive z-axis. So if I had chosen the z-axis to be into the paper here instead of out of the paper, would be an improperly defined coordinate system. That is, say it wouldn't be right-handed, and it would lead to some difficulties later on. We want to always make sure we've defined the motion of the particle in terms of a right-handed coordinate system. This one is a Cartesian coordinate system. The position vector then has an x component, so we write r, the vector, equals x in the I direction. The I unit vector again points in the direction of the x-axis, plus y, this component, in the j direction, times j unit vector, plus z, the component of the position vector in the z direction, times the k unit vector, a unit vector pointing along the z-axis. The time derivative of the position vector is the velocity vector. Taking the time derivative of these terms and remembering that the time derivative of I is 0, we get x dot I plus y dot j plus z dot k. The other terms that have not been written because they're 0 would be x times the time derivative of I with respect to t plus two other terms. But in the Cartesian coordinate system, that term is always 0 because I is fixed. It always points north, if you will, and it always has magnitude 1. The acceleration vector is equal to the time derivative of the velocity vector, which, again, because I, j, k are fixed vectors in magnitude and direction, is x double dot, the second derivative of x with respect to time, I, plus y double dot j, plus z double dot k. In cylindrical or polar, usually they're called polar in the case of two-dimensional coordinates, or cylindrical in the case of three-dimensional coordinates. So I'm showing the more general case here of cylindrical coordinates. We have, with respect to the original XYZ Cartesian coordinate system, we have a position vector r that's made up of a magnitude r in the ER direction. ER is now a unit vector along this line of the position vector r to the particle. Okay? Plus, and I'm doing this all wrong. I need to make a correction here. This is not correct. ER is in, I'm going to, well, it is correct if we remember that that's in the plane. This is in the plane of XY. Okay? It's so that this dashed line is the projection. I didn't show R on here. R is comes out of the XY plane. So the actual position vector is to this blue, if you're seeing this in color. The actual position vector is to the particle. The projection of that vector on the XY plane is R, so that R, the vector is equal to that magnitude there, R, and that's not the magnitude of this. We might want to introduce some other notation to emphasize that. Let's call this position vector here. Well, I'm just going to put a little asterisk out here to remind you that the usual notation would be this is the magnitude of that, but that's not the case here. R is the magnitude of the component in the XY plane. So the position vector is R in the UR direction, or ER. I think our handbook uses ER there, but it means the same as UR, a unit vector in that direction in the XY plane, plus Z, the component of the position vector perpendicular to the XY plane in the K direction. Now K is the same unit vector we introduced in Cartesian coordinates, that is, it is fixed in direction and fixed in magnitude. But this unit vector ER, while it is fixed in magnitude, like all unit vectors, does change direction as the position of the particle moves, because ER at one point points in this direction and at another point points in this direction. So that's going to enter into our time derivatives of the position vector. Now, planar motion is what we're interested in. In planar motion, when the particle remains in the XY plane, we forget about this term, okay? Z is always 0, and we have a simpler expression for position vector. The position vector R is now R in the ER direction, and R is here the magnitude of this vector. Continuing, with polar coordinates again, two-dimensional, the velocity vector is the time derivative of the position vector, which is equal to R dot ER plus R times the time derivative of the unit vector ER. And it can be shown that the time derivative of ER is theta dot E theta, where theta is the angle in the XY plane measured from the x-axis to the vector projection of the vector, or in polar coordinates, the vector itself in the XY plane. E theta is another unit vector introduced such that it's perpendicular to ER and points in the direction of increasing theta. When you define E theta that way, the time derivative of ER is theta dot E theta. Theta dot's expressed in radians per second, so that is this has units of 1 over seconds, which is the proper units for the time derivative of something that's non-dimensional. The velocity vector is then R dot ER plus R theta dot E theta. And this term arises from the fact that I've emphasized that ER varies with time. It varies with position, and the position varies with time, so ER has a time derivative. In the Cartesian coordinate system, that term is always 0, but in cylindrical coordinates, the term is important. Similarly, we can show that the acceleration vector, which is the time derivative of the velocity vector, leads to these terms. R double dot, let me skip the details. You can study those. It leads to this component in the R direction. R double dot minus R theta dot squared. That's an R omega squared term, which sounds familiar to you. That's the acceleration of the particle back toward the origin in the opposite direction of ER. And this is the acceleration of the particle that results from the fact that R itself might be increasing at an increasing rate. And in the theta direction, R theta double dot, that's sometimes we say R alpha. This is an angular acceleration of that line. And we have a 2 R dot theta dot. The R dot theta dot term is an interesting one that we refer to as Coriolis acceleration. It has some interesting attributes, but beyond the scope of the study here. Okay, the third coordinate system we want to talk about are path coordinates. At least that's what I call them: normal and tangential. The way they are defined is at any point on the path, and that's why they're called path coordinates. The path itself can be approximated at that point as a short circular arc which points to some local center of curvature, which has some local center of curvature. The normal unit vector is directed inward toward the center of curvature. The tangential unit vector is directed perpendicular to the normal unit vector in the direction of the velocity vector. So the tangential vector points in the direction of the instantaneous velocity. The normal unit vector points in the direction normal to the curve, toward the local center of curvature. And we don't start as we did before by writing the position vector. There is no expression for position vector in this coordinate system. There's an expression only for the velocity and acceleration. The velocity vector is easily written since it is equal to since it's in the same direction as ET by definition. It's equal to the speed v times the tangential unit vector E sub t. So that's the starting point in our kinematics in the path coordinate system. So we will take the derivative of the velocity vector to get the acceleration vector. If v is equal to the velocity vector is equal to the speed times the tangential unit vector, then the acceleration vector is the time derivative of v times et, because the law of taking derivatives here, the law of products, and then it's plus v times the time derivative of et. And we can show, I won't do that here, we can show that the time derivative of et is v over rho, where rho is the instantaneous radius of curvature, that is the distance from the particle to the instantaneous local center of curvature, and v is the speed. So the time derivative of E sub t is, as the time derivative of all these other unit vectors, a vector that's in the perpendicular direction of E sub t, and it has magnitude v over rho. If you look at the units on that, you'll find it's the appropriate units. It's 1 over time. This is length per time. This is length. So the units of this time derivative of this unit vector are 1 over time. Then the acceleration becomes v dot et, which is the acceleration along the line of travel, the path, in the tangential direction, plus v squared over rho in the normal direction. And remember, normal direction points toward the center of curvature. Okay. With that, we have developed a basis, reviewed the basis for particle kinematics. So I'm going to go over a couple of example problems that will indicate some of the concepts that you'll probably have to understand to pass the fundamentals of examination. This problem is from the textbook here, the EIT review manual, And when it just gives you a page like that, that's the reference we're referring to, so you can look it up, see more details. But this is rectilinear motion of a particle. If we're given S, the position along the path in terms of time, where S is going to be expressed in meters and T is in seconds. So obviously this 20 is going to have units of meters per second, but they're hidden. We can find the initial velocity, the velocity at time 0, by taking the time derivative of S, which is 20 plus 8t minus 9t squared, and substituting t equals 0, so that we have 20 plus 0 are 20 meters per second. We're also asked in the second problem to find the acceleration at time 0. To find the acceleration at any time, we take the time derivative of the speed, dv dt, and remember the speed is 20 plus 8t minus 9t squared as a function of time. So taking the time derivative of that function of time, we have 8 minus 18t. Plugging in time t equals 0, that's the time we're asked to find the acceleration. We find the acceleration, initial acceleration, is 8 meters per second squared. A common error that my students make, I'll tell you so you guys don't make this, is to try to compute the time derivative of the velocity at 0, not the velocity at time. You see, what we did is we computed the time derivative of the velocity as a function of time. Okay, we took the derivative of this function, not this value of the function. If you try to take the time derivative of 20 meters per second, for example, you would conclude that the initial acceleration is 0, and you can make a similar mistake up here in this. I've seen students plug in t equals 0 and then take the time derivative and conclude that the initial velocity is 0. So remember not to make that common error. The third problem is for the same particle motion, and we're asked to find the maximum velocity. Remember, we just got through calculating the velocity as a function of time and the acceleration as a function of time. Remember, the maximum velocity occurs when the derivative of the velocity, which is the acceleration, is equal to 0. So we set the acceleration equals 0, and we saw for some time, I've called it here t prime, at which the acceleration is 0, and therefore at which we can find a maximum or minimum velocity. If I set this equal to 0, and I solve for t prime, 8/18 or 4/9, I find the 4/9 of a second is the time of 0 acceleration or maximum or minimum, we don't know, velocity. And if you plug in this time t prime back into the expression for our velocity, you get 20 plus 8 times 4/9 minus 9 times 4/9 squared. You get 21.8 meters per second, which is the maximum speed. Okay, another problem of particle motion. This is one in which the motion is more general. That is, it's not rectilinear. It's a more interesting problem. Perhaps for the benefit of anyone else viewing this tape, the initial presentation is for troops at Fort Hood, so perhaps you're more knowledgeable there about the range of cannons than I could be. But this is the way you'd approach the calculation of the particle velocity of a projectile fired with some known initial velocity in the absence of aerodynamic resistance. So it's a very simplified problem, but it's illustrative of how you can solve projectile problems, the kind you'll be expected to solve on the EIT. This is problem 6 on page 14-5. We're given artillery on the high ground here, 1,500 meters, that fires a projectile with a muzzle velocity of 1,000 meters per second, and that's a pretty powerful cannon, it would seem to me, at 30 degrees above the horizontal. We're asked to find the range, and the range is, of course, the value of x if we introduce a coordinate system that has a reference at say the cannon. It's the value of x when the projectile strikes the terrain out here. We're going to neglect aerodynamic resistance, and we know the acceleration of the particle because we know it's in a gravitational field. There are some clues here about what coordinate system we want to use. And these are the kind of clues I'm going to try to emphasize throughout the presentation, because I think this is probably the most important part of what I can tell you. There's lots of ways to approach each of these problems, but there's usually a clue that tells you what's the best way. Is the path known? We don't know the path. We don't know an equation for the path. We don't know much about the path. You might guess that it's a parabola, but that's just because you have some experience in physics. But the path is not known. Is there cylindrical geometry involved? If it were moving in a circular path, if that were known, we might choose to use polar coordinates. But because the answer to those is both no, the clue is that we want to use a Cartesian coordinate system. Okay, that's how I determined that. The blue stuff is what's given to me in the form of the problem, and I put on here the red marks that indicated I'm going to introduce at the muzzle of the cannon a coordinate system with a Cartesian coordinate system, x being in a horizontal direction, y being up. I could have chosen down. I've recognized that they want me to put gravity in that direction, and I've recognized that the acceleration is minus g in the j direction. It's downward of magnitude 9.81 meters per second squared, or 32.2 feet per second squared. Since the muzzle velocity is given in SI units, we'll be using that value. If there were air resistance, see, there would be another force on a projectile, and the acceleration would be something different from this. So we're neglecting air resistance. If we have air resistance, this is a problem we'd have to, would be much more complicated. It wouldn't be a kinematics problem. It's a kinematics problem here because we know the acceleration. We're going to integrate that to get velocity in position. Okay, starting off with the acceleration vector, A is equal to minus GJ. And it certainly isn't necessary to do this in vector notation. If you write scalar equations, you're going to write an x and a y component of this equation. AX is 0, AY is minus g. Okay? The velocity vector is obtained by integrating the acceleration. In other words, dv dt is a, so dv is equal to the integral of a dt. And this is where I'm emphasizing that the importance of initial conditions. Okay, this is dv, not just v. Okay. I've got these two pages out of order. Let me renumber this one 15 and this one 16. Let's look at 15 first. Looks like I have them out of order. Okay. Okay. The velocity at any time t is the integral from 0 to t of a of, this technically should be some other variable, say t hat, dt hat. That's a dummy variable. T is the value of time, and I'm not going to worry too much about that in the future, but I'm just emphasizing that to be mathematically precise, we ought to call that tau or something else. I've tried to write tau down here. Okay, integral from 0 to t of acceleration plus the initial velocity vector. So the velocity is v naught, the initial velocity vector, plus integral from 0 to t of minus g times the j unit vector, d tau, or whatever dummy time variable I'm using there. V naught is 1,000 meters per second times cosine 30 degrees in the I direction, plus 1,000 meters per second times sine 30 in the j direction. You know how to resolve a given initial velocity vector into x and y components, minus this term here integrated is minus g times j times t. So v is 1,000 cosine theta I plus 1,000 sine theta minus 9.81 meter per second squared times time in the j direction. That's the velocity vector for all times after the cannon is fired. It tells you the position of the projectile at all times. We can integrate it in the same fashion to come up with the position vector for all times. Since r is the integral of dr, which is integral of v dt, which is equal to r naught, which is 0, plus the integral from 0 to t of the velocity vector at some time tau, dummy variable tau, d tau. R naught is 0 because it chose my coordinate system at the muzzle of the cannon. Then the position vector r is the integral of 1,000 meters per second cosine theta I d tau plus, that's the I direction, plus in the j direction 1,000 sine theta minus 9.81 tau d tau. Somewhere I better write j to be correct. Okay, I'll put it there. And integrating that, we get this expression for the position vector. 1,000 meters per second cosine theta t. So if t is in seconds, this is going to give you a value in meters in the I direction, plus 1,000 sine theta t minus 9.81 over 2 t squared in the j direction. Okay, what does range mean? That's what we're asked to find. It means the value of x when ry is minus 1,500, because when ry is minus 1,500 meters, it's going to strike the ground. So we set ry, which is 1,000 sine theta t minus 9.81 over 2 t squared equal to minus 1,500 meters. And we solve the resulting quadratic equation in t for the time that the projectile strikes the ground. And we get two roots. We get 104 seconds, 105 seconds, and we get minus 2.9 seconds. Well, the root we're interested in is 104.5. The meaning of the negative root is if the projectile were on this trajectory, it would, if it had started back here at ground level, at elevation minus 1,500 meters, at a certain value of x, a negative value of x, it would pass exactly through this point at time 0, and it'd be on the same trajectory as the projectile that we've fired. So that's the meaning of that negative root. Of course, it's easier to just say that we're not interested in it, and we're going to take this value of 104.85 seconds and plug it into our expression for x as a function of time. 1,000 cosine 30 times t, and we have 90,803 meters, 90 kilometers. So that's a big cannon. Okay? I just might point out that we neglected air resistance, remember. A more practical problem, which is beyond the scope of this review, would include some aerodynamic resistance. And usually you'd have another acceleration term. This gets into dynamics, but you're going to have an acceleration term that's in the direction of the velocity vector, okay? And it's got some magnitude, which we might say the drag, divided by the mass. But the point is, that acceleration is not in the x or the y direction. It's in a direction that varies as a function of the direction of the velocity. But the end result is that you expect with aerodynamic resistance, you're going to reduce your range like that, of course. Okay, let's talk about another example. Again, an example of kinematics. This is problem number 3 on page 14-6 of Lindbergh's review manual. We're given a reciprocating pump, so there's a piston here. Probably the piston is closed, so we can compress something. The cylinder is closed, rather, and the piston moves back and forth in the cylinder. The rotation of the crankshaft here is given 350 revolutions per minute. We're going to have to correct our units, of course. or the length of the crank throw is 0.3 meters, about a foot. And what we're asked to determine is the velocity of point A at a certain angle of theta. So actually, we don't need to know much about the piston, the connecting rod, and the piston. We're really just looking at the rotation of a crankshaft to point A, a distance 0.3 meters from the crank, center line of the crank. The clue is the fact that we have cylindrical or polar geometry. We have a particle moving in a circular path. Particle A moves in a circular path, centered at the center line of the crankshaft, and that suggests that it's going to be advantageous to us to use polar coordinates. Remember, in polar coordinates, the velocity vector is equal to r dot in the ER direction plus r theta dot in the E theta direction. Okay? The R direction is outward. Let's see, let's draw the center of the crankshaft and point A. Then this is ER, okay? And it's rotating in that direction, so E theta is, and theta is measured here. So E theta is this direction. And the velocity is r dot, ER, plus r theta dot E theta. Notice that r is fixed, okay? So the time derivative of r is 0, so this first term is 0. There is no velocity in the radial direction, which should make sense to you intuitively. The only velocity is going to be in the E theta direction, and its magnitude is r theta dot. Theta dot is the angular speed in radians per second of the crankshaft. We calculate that by 350 revolutions per minute, RPMs, times 2 pi radians per revolution over 1 minute in 60 seconds to get 36.65 radians per second. Usually we just write that as 1 over seconds. That's the value of theta dot. Then the speed v, the magnitude of the velocity vector, in this case, it's a component of the velocity vector otherwise, but here it's the magnitude of the whole vector, is 0.3 r, 0.3 which is r, times 36.65 radians per second, or 10.996 or 11 meters per second. And the answer is D. Another problem, problem 5 on page 14-6. We're given a disk that rotates about this axis B through B with respect to the link AB, and we're interested in finding the maximum velocity of any point on that disk. It's left to us, and then the blue here shows what the way I've worked the problem. It's left to us to identify the point where the maximum velocity is going to occur, and it's intuitive here that since it's rotating in this direction and the link is also rotating in that direction, the maximum velocity is going to be point C out there. By inspection, point C will have maximum velocity. And the velocity of point C, this is a notation indicates relative velocity. The velocity of point C is the velocity of point C with respect to point B on this member, plus the velocity of point B, both of which we can compute by kinematic equations that we have developed or reviewed earlier. And of course, you should always plan ahead and never try to write something like that at the bottom of the page. Rewriting. Velocity of C with respect to B is 1.75 meters. Okay? That is the radius here. So we have this distance is 1.75 meters times the angular velocity of the disk. Now the wording of the problem is a little vague. It says the disk rotates counterclockwise 60 RPMs relative to the link, and the link rotates 12 RPMs counterclockwise itself. So the angular velocity of the absolute angular velocity of the disk is 60 plus 12 RPMs. We multiply by 2 pi over 60 to convert that to radians per second, and the radius of 1.75 meters times the angular velocity of the disk gives 13.195 meters per second. That is the relative velocity of point C with respect to point B. Now, point B is itself moving, so we got to add the velocity of point B to this term to get the absolute velocity of C. And to calculate the velocity of point B, we observe that it is 12 meters from a fixed point A, so its velocity is that distance times the angular velocity of the link, which is theta dot. This is r, theta dot. 12 revolutions per minute times 2 pi over 60 to give us radians per second, which is 15.08 meters per second. So I'm going to add the 15.08 and the 13 using this equation to get the velocity of point C, 28.27. The answer is B. Lindbergh works this problem in the manual, and he gets the right answer. But the solution's a little misleading. He's using a technique that is certainly valid, but it's more advanced than his review would indicate is something you'll need. He's using a rotating coordinate system, and so if you have trouble following his example, you might try to compare it to the example here and see if you understand the difference. But it's a little misleading. It's a solution using a more advanced technique than we've reviewed today, or that he reviews. Okay. Another example problem. We're given in problem 10 and 11 on page 14-7 of Lindbergh the position in radians of a car traveling around a curve. Theta, as a function of time, is t cubed minus 2t squared minus 4t. And this better be in units of radians, non-dimensional. Okay? That is to say, the 4's got to have units of radians per second. The 2's got to have units of radians per second squared. The 1 in front of the t's got to have units of radians per second cubed. The clue, or the hint, is they tell us one of our polar coordinates, theta is a function of t. Okay, we don't know the path, so we're not going to be using path coordinates. It's not convenient to use Cartesian coordinates. The clue is to use polar coordinates. You need to learn to recognize the clues that are in the problems to work them most efficiently. We're asked to find the angular velocity, and this is a little perhaps not a good term. He wants theta dot. That's what he's asking for. Now, we're talking about a particle here, and everybody knows particles don't have angular velocity, right? They can't. They're points. They don't spin. So angular velocity is really not the right term to use there. Probably he should just say find theta dot, or maybe he should ask find the rate of change of the angular coordinate or the angular speed, rather than the angular velocity. But that's what he's asking you for. Well, we don't have to do that. This is just a review of the kinematics. Theta dot is d theta dt. Taking the time derivative of the given expression of time, we have theta dot is 3t squared minus 4t minus 4. Plugging in 3 seconds into that expression, we have minus 11 seconds, minus 11 radians per second, which is the value of the rate of change of that angular coordinate. The answer in the book then is C. Okay, we've reviewed several kinds of kinematics problems. We'll be going back to kinematics from time to time, but I want to take up a review of dynamics or kinetics. And let me emphasize, the reason we break down the study of dynamics first into kinematics and then more broadly into kinetics or dynamics is to isolate an important part of the problem, which is the kinematics, without confusing us with the physics of motion or the kinetics. But now we're going to talk about more general dynamics problems, which we sometimes call kinetics. A couple of definitions here, or one, I guess. The momentum of a particle, so we're really talking about particle kinetics here right now, at first. The momentum vector, and I put a vector sign over momentum to emphasize that it's a vector, is defined as the mass times the velocity vector. So the momentum vector we call P always points in the same direction as the velocity vector. It has units of mass times velocity, or meters per second times, kilograms meters per second. Newton's second law says that the forces that act on a particle, it's a vector equation, is equal to the time derivative of the momentum of the particle, or the time derivative of the mass of the particle times its velocity vector, and in the special but very important case that the mass of the particle is not changing with time, it's equal to mass times acceleration. Almost always you write and use sum of forces as mass times acceleration. But if you're interested in predicting the motion of, say, a rocket, okay, whose mass is changing with time because the fuel is being burned and ejected out the rear of the rocket, then you want to remember that this form of Newton's second law, which is more fundamental, is what has to be applied in those problems. And it makes the problem very interesting. But we're going to be primarily talking about particles whose mass doesn't change, so we'll write some of the forces as mass times acceleration. Okay, some units. Most of the problems, I understand, perhaps all, on the EIT examination can be worked in SI units. Okay, SI, metric units, have length units of meters, time units of seconds, mass units of kilograms, and shown here in parentheses in red for emphasis is the derived unit that's a Newton. Okay? By comparison, the US units, sometimes called the English engineering system, the length unit is a foot, the time unit is a second. There's a difference in the way we abbreviate units in these two systems, incidentally. Thank goodness we at least have the same time unit, right? The force unit is a pound, and the mass unit is a slug. Now, that's a derived unit. The basic units in the US units are length, time, and force. The basic units in the SI units are length, time, and mass. Both of these two systems of units are what we call consistent systems. And it's important to understand the difference here. A consistent system of units is one where the unit of force, I'm not writing F equals ma, I'm not writing Newton's second law, I'm just saying that in a consistent system of units, the units of force are equal to the units of mass times the units of acceleration. For example, 1 pound, the unit of force, is equal to the unit of mass, 1 slug, times 1 foot per second squared. Okay, so a pound force will accelerate a slug 1 foot per second squared. A slug is 32.2 pounds mass, as you know. We'll talk about what a pound mass is in a minute. I probably shouldn't have brought that up just yet. A Newton, in the SI system, a Newton force will accelerate a kilogram mass 1 meter per second squared. Whenever this unit force accelerates a unit mass, a unit acceleration, the units are said to be consistent. And in those two systems of units, they are consistent. You will notice if you look in your in the two references, this one and this one, from time to time they'll write a gravitational constant, G sub c. And if you use consistent units, you don't need a G sub C. I'll say more about that later. Further, some will write pound force and pound mass to distinguish between force and mass units. In my notation, pounds will mean force. Okay, I probably won't write pound force. If I write pounds, I'm talking about force. If I want to use pound mass, the unit of pound mass, I'll write pound mass. Okay, we haven't introduced what pounds mass are. Let's talk about that. A pound mass is that unit of mass that has the weight 1 pound force. Okay, so if you carry as many car keys as I do, I like to remember saying that, and sometimes a visual reference is good. My car keys weigh a pound. Okay, therefore they have a mass of 1 pound mass. If they had a unit of mass of a slug, I'd have trouble carrying them around. That'd be 32 pounds force. Okay, a slug is 32 pounds mass, and it would weigh 32 pounds force, right? The definition of weight is mass times gravitational acceleration, mg. So that's the force that an object of mass m would exert on a spring balance or any other kind of balance in a gravitational field of magnitude g, which is the standard is at the Earth's surface. Now let's talk about this system of units that we've hinted at. The U.S. it's called the U.S. customary system of units, with a length unit of a foot, time unit of a second, and a force unit of a pound force, and a mass unit of a pound mass. It's not a consistent system of units. Okay, that doesn't mean you can't use it. It just means you have to have a little correction factor, so to speak, because the units of force are not equal to the units of mass times the units of acceleration. Okay, Newton's second law still applies, but the unit force, 1 pound force, does not accelerate a unit mass, 1 pound mass, 1 foot per second squared. So the system is not a consistent system. In order to use it, wherever you see mass, if it's expressed in pound mass, you got to throw in a G sub C, gravitational, gravitational constant. Okay? Now, G sub C is not 32 feet per second squared or 9.81 meters per second squared. It's 32.2 or 32.18 pound mass per pound force second squared per foot, or 9.81, well, I'm sorry, forget that. It's not 9.81. It's this value right here for that system of units. Whenever you use this system, if you are going to use pounds mass, then you need to use, instead of mass, you need to use mass over G sub C, where you have to remember this value of G sub C, or find it in the handbook. Okay? So, in summary, the 3 systems of units that might come up in our discussion are these 3. The SI system, which is going to be the most important system of units in this review. The length units are meters, the time units are seconds, the mass units are kilograms, and the derived force unit is newtons, and G sub C is 1, okay, because it's a consistent system of units. So that whenever you write F equals MA, you don't have to divide by a G sub C. And the US English engineering system has units of length equal to foot, units of time equal to second, units of force equal to pounds, or pounds force if you want, and the derived unit is a unit of mass, which is a slug. Okay? And it's a consistent system, so you don't need a G sub C. If you're going to use the U.S. customary system, the units of force, units of length are foot, the units of time are seconds, the units of mass are pounds mass instead of slugs. So this unit here is different from that. A slug is 32 times as big as a pound mass. The same force units, pounds, you have to have a G sub C. Wherever you use mass in an equation of mechanics, you would use M over G sub C, and the G sub C you use is that value right there, 32.18, that should say, pounds mass, feet per pounds force, second squared. This is not a consistent system of units. Okay. As I said, the definition of weight is the force that would be exerted on a given mass in a gravitational field equal to that on the surface of the Earth. So we write weight is mass times g, where here g, this is not g sub c, this is g, the acceleration of gravity. It's going to have acceleration units. G is 9.81 meters per second squared, or 32.2, or 32.18, at your pleasure, feet per second squared. Example. The weight of one slug is, W, is one slug times 32.2 feet per second squared, that's G, okay, is 32 pounds. So a slug weighs 32 pounds. The weight of 1 kilogram is 1 kilogram times 9.81 meter per second squared, that's the acceleration of gravity, SI units, is 9.81 newtons. The weight of a pound mass is 1 pound mass over G sub C, which is 32.18, okay, times G, which is 32.2, is 1 pound force. So a pound mass weighs 1 pound force, a slug weighs 32 pounds force, a kilogram weighs 9.81 newtons. Another concept that's important to us in dynamics is friction. And basically we use the law of Coulomb friction to model this frictional phenomenon. The law of Coulomb friction, or dry friction, says that the friction force is less than or equal to mu n. Sometimes we think F is equal to mu n, but generally speaking, the friction force can be any value up to and including mu times the normal force. And we usually think of mu being in the range 0 to 1, right? But I guarantee you, if you want to either convince yourself that mu can be bigger than 1 or the law of dry friction doesn't apply to such, calculate the coefficient of friction for your favorite drag racer in accelerating him down a quarter mile in whatever time he does it in, and you'll find that mu between his tires and the road is considerably bigger than 1. So, in the problems you'll be given, I think what that really says is dry friction doesn't apply to drag racers because the tires adhere to the road. But the point is, this is just an empirical law that we model frictional interaction between certain kind of surfaces. If there's Scotch tape under there, then there's adhesion at work, and the law of dry friction doesn't apply. Here's a free body diagram of a block on a plane with a frictional force. Notice that the block is constrained to move up and down the plane. Gravity acts in this direction. And this being rectilinear motion along an x-axis, we can introduce an axis in this direction, and we then don't have any motion in the perpendicular or y direction. So the equation of interest to us is for motion is going to be in the x direction. But we're going to learn something from statics here in the y direction. The summation of the forces in the y direction is 0 because all the motion is in the x direction. Okay. Notice that, let's say a few words about free body diagrams, this being the first chance we've had to talk about them. A free body diagram isolates the object from its environment. You see, I've taken the block here, I've removed the environment, which is the plane, and I've replaced the environment with forces that represent the same effects. The weight, of course, acts due to gravity, and that is present, but the plane causes these two interactive forces. A normal force, called normal because it's in the normal direction, it's perpendicular to the plane, and a frictional force, which can be as big as mu times the normal force. Okay. In the normal direction, the summation forces equals 0 says that n minus w cosine theta is 0, or n, the normal force, is equal to w cosine theta. Theta is this angle of incline of the plane. So we can calculate the normal force knowing that the object is in equilibrium in the y direction. Okay, then the frictional force is equal to or less than mu n. For small values of theta, okay, there might not be a very big frictional force required to prevent slip. and the only frictional force that's needed is that required to prevent slip. If you say force is equal to mu n, then you might cause that block to be accelerated up the plane by the frictional force. We know that doesn't happen. Okay, another concept of friction that's sometimes introduced here we need to know about is the difference in the static coefficient and the kinetic coefficient of friction. And this sketch is in Lindbergh's manual, and it's a little confusing. But what he's trying to illustrate is that if you talk about the resisting force and the disturbing force, the resisting force being friction and the disturbing force being whatever's trying to move this along the plane, gravity. In the case of if you keep increasing the angle of the plane, gravity is trying to cause it to move down. So as gravity increases, the disturbing force, as you increase theta, the resisting force is also increased, preventing it from moving, up to the point where you reach some critical angle theta, and the frictional force can no longer be, when the frictional force is equal to mu n, it can't get any bigger. So if you make the angle of the plane greater than that critical angle, it's going to start to slip. Well, the static coefficient of friction and the kinetic coefficient of friction are two frictional coefficients that are introduced because it's observed that once the block starts to slip, the frictional force drops a little bit. So it takes a force greater than mu s, the static coefficient, times n, to cause it to slip. It'll resist that much. But once it starts to slip, then the maximum the force can be is mu k, the kinetic coefficient of friction, some smaller value, times n. And then you have motion. So mu s, static, and mu kinetic coefficient of friction times n are these two values here, and that's what he's trying to illustrate with that sketch in the book. I already mentioned a free body diagram. Let me say it again because this is very important. A free body diagram is all the forces that act on an isolated body. You can apply to your free body diagram Newton's second law. Some of the forces is mass times acceleration. Remember, that's if the mass of the body is not changing. And the free body diagram is the recipe that you're going to write the equations of equilibrium or motion from. So you got to have your cookbook, so to speak, your recipe, your free body diagram before you get the right equation to solve. So please do sketch, even for simple problems, please do sketch free body diagrams. Instantaneous center is a concept from kinematics, and I guess I didn't know where to put this in. The definition of the instantaneous center, got nothing to do with forces, we're back to kinematics, is that point about which at any instant, okay, a body is rotating. And you can locate it by finding the point of intersection of two lines which are perpendicular to two velocity vectors of 2 points on the body. As an example, and this example is in the book, I didn't make note of the page. If you have a connecting rod AB and a crank OA that's rotating, and the piston B is moving up and down, the connecting rod AB has an instantaneous center that's located by first observing that the velocity of point B is in that direction. It's got to be, because the piston's moving only up and down, right? It's either up or it's down, and it doesn't matter which. And the velocity of point A, since it's constrained to follow a circular path by this crankshaft, has to be tangent to that path. So it's either that direction or this direction, depending on which way the thing's rotating. So if we draw a perpendicular line from this velocity vector and a perpendicular line from this point, a line perpendicular to its velocity vector, they intersect at some point out here C, which may not be a part of any of the body in question. It's a point in space. At this instant, when the A is here and B is here, we can say that bar AB is instantaneously rotating about point C. And that's a useful tool in the study of dynamics problems sometimes. Okay. Back to kinetics. We went to a lot of trouble when we were studying kinematics to learn how to calculate accelerations and velocities and positions, either from position vectors that are given or from accelerations that are given. The reason we did that is because here in dynamics, when we write down the forces, we can use Newton's second law to allow us to solve for the acceleration. So if all the forces are known, then the acceleration vector is known. And if that's the case, we'll be performing kinematics exercises from there on. The dynamics part is right here. Then the kinematics is, given the acceleration vector, determine velocities and positions. That's why we studied kinematics for so long, is because this much, of the problem is kinematics, and this much is physics, or dynamics. And just to refresh your memory, we looked at kinematics of 3 different coordinate systems. The corresponding kinetics equations would be the summation of forces in the x direction is mass times acceleration in the x direction. Similarly in the y direction and the z direction. Those are the expressions of the components of Newton's second law in Cartesian coordinates. And then we would do, as we indicated in our study of kinematics, we could calculate the velocities and the positions. In polar coordinates, the summation of forces in the radial direction is the mass times acceleration in the radial direction. And the summation of forces in the theta direction, transverse, is equal to the mass times the, I guess that would be tangential, would it not? No, transverse. With mass times acceleration in that direction, in the theta direction. And then, once we know the acceleration in the radial direction, we set it equal to, from kinematics, r double dot minus r theta dot squared. And when we know the theta component of acceleration, we set it equal to r theta double dot plus 2 r dot theta dot. And integration of those is a little trickier. In path coordinates, the equations of kinetics say that in the normal direction, the summation of the forces is mass times acceleration in the normal direction. And in the tangential direction, summation of forces is mass times acceleration in the tangential direction. Once we've calculated normal and tangential accelerations, we recall that v squared over r is the normal component, and v dot is the tangential component of acceleration, which would allow us to solve for v and the position. Well, just so you'll know your notes are complete, I've got page 34 here that's blank for some reason. Probably was going to say something very profound there and never figured out what it was. So we're on page 35. An example problem. This is problem number 1 on page 16-5 in Lindbergh's book. We're given a 2 kilogram mass which swings in a vertical plane at the end of a 2-meter cord. We're asked to compute the tension in the cord. We're also given that the magnitude of the tangential velocity is 1 meter per second at the position theta equals 30 degrees. To find the tension in the cord, we're first going to draw a free body diagram. From this sketch of the problem, with theta identified like that, the free body diagram now, I'm going to draw a free body diagram of the mass. So I've removed the cord. Okay, I've cut it, and I've replaced the cord with the effect that the cord has on the mass, which is the force T, the tension. And I've included the weight, G being downward here, and that's a free body diagram. It's complete. I haven't left anything out. If there's magnetic forces or aerodynamic resistance or something, I don't know about them. I've left those out. I've neglected them. If they're present, we have more forces. From kinematics, remember that the normal acceleration is v squared over rho. Okay? The normal tangential coordinates are suggested by the problem here because this thing moves in a known, well, we could use path coordinates. I guess that's what those are. Yeah, it moves in a direction, in a known path, so that the normal direction is known. The r, the radius of curvature of the path, is known at every instant, and that suggests to us that we're going to be productive using path coordinates. Okay, Newton's second law says that the summation of forces on our free body diagram is mass times acceleration. Let's see. Let's keep this handy. In the normal direction, that is to say, this direction, En. Okay, I have T minus W cosine theta. This angle is theta. Okay, is equal to the mass times the acceleration in the normal direction, which by kinematics is v squared over rho. Okay, so the tension is equal to W cosine theta plus mv squared over rho. Let's see, forgot what they told me was given. Magnitude of tangential velocity. Okay, so we know v. We know that v is 1 meter per second. We know the radius is 2 meters. We know the angle is 30 degrees. We know the mass. We know G. We know W. W is mg, right? This is W. W is in newtons. I don't worry about checking my units. I know that if I use consistent system of units, when I calculate T, I'm going to get the basic unit in the consistent system of units in SI units, newtons. I get from the first term, W cosine theta, 16.991. From the second term, mv squared over rho, 1. 17.99 or 18 newtons is the tension in the cord. Most of the tension is due to the weight of the particle. Okay, it's 2 kilograms. It weighs 19 or nearly 20 newtons. At 30 degrees, the effect of that weight is to cause 17 newtons of tension in the cord. Only 1 newton of tension is caused by the speed. If it were moving faster, if the angle were different, it might be that most of the tension, even all of it, is due to v squared over rho. In a similar example, this is problem 2 on page 16-6. A 2 kilogram mass swings in a horizontal circle. So now we don't have gravity. This is on an air table or something, moving horizontally. Of radius 1.5 meters, it's held by a taut cord with a known tension. So we don't know the radius, but we know we do know the radius. We don't know the speed, but we do know the tension. We're asked to find the angular momentum of the mass. I've emphasized in red about the center of circle. Its angular momentum is defined as r cross mv, and I didn't find that in the handbook, so it may be that this problem wouldn't be on the fundamentals exam, but Lindbergh thinks it might be. The definition of angular momentum is r cross mv. And of course, r depends on, it is a position vector from some point to the particle. Well, to ask you to compute the angular momentum of the mass requires them to tell you what point they want you to compute it about. It's pretty obvious they want you to compute it about the center where the card is held, and that's what I'm going to do. So I'm assuming that they want us to calculate it about the center of the circle. This is a little free body diagram here. Now here gravity is down. The motion is in a horizontal plane. So there must be some support, say N, that holds this thing up. So if it's on a slick surface, N, there's no friction. N resists W, and N's equal to W, right? So the only force in the horizontal plane is T. And T points in the normal direction back here towards the center of the circle. The summation of forces in the normal direction is mass times acceleration in the normal direction. T in the normal direction is equal to mv squared over rho, which is acceleration in the normal direction. So v squared I can determine to be T, solving this equation, T rho over m, where rho is the radius of the cord, 1.5 meters, T is the known tension, 100 newtons, and m is the mass in kilograms. I don't have to worry about those units they're going to come out in units of speed, meters per second, in the SI system, since that's a consistent system of units. V is equal to square root of 75, or 8.66 meters per second. That's the speed, not the angular momentum. Now, R cross mv is the definition of angular momentum. R from the center of the circle to the particle is going to have a magnitude of 1.5, and since the speed of the particle is perpendicular to the string, R cross mv is just going to be equal to, in scalar form, R times mv. Okay? So the angular momentum, which is sometimes denoted H, is R cross the linear momentum, or R cross mv. I've done it in vector form here to give you something to study in case you want to do that, but the scalar calculation is very straightforward. Linear momentum is P is equal to mv, which is the mass 2 kilograms times the velocity 8.66 meters per second squared in the tangential direction. Okay, it's rotating in such a way that its velocity vector is always in the tangential direction. R is minus 1.5 meters in the normal direction. So R is from the center out, and so it points outward, and En points inward. So R is minus 1.5 meters En. R cross P is then minus 1.5 meters times 2 kilograms times velocity, mass times velocity, times E sub n cross E sub t. Well, notice that E sub n cross E sub t by the right-hand rule is going to be a vector that points down. Okay? And so that's minus E sub z, or minus k if you like. And I've got a minus sign here and a minus sign there. So R cross P is 25.98, or 26. You don't have to worry about the units if you stick with consistent units. 26 units of angular momentum, which is units of momentum, meters per second. Okay. No, I'm sorry. Newton. It's Newton meter seconds, like I had. It's mass, which is kilograms, times speed, meters per second, times radius, meters. Kilogram meter squared per second. Or, that's the same units as Newton's meter seconds. I know that because this is units of force, and this is units of, I'm sorry, Newton seconds is units of impulse. Okay, and meters is units of distance, and so that's an angular impulse. But either set of units would work. Either expression for units would work. They're identical. Newton meter seconds or kilogram meter squared per second, and you can work that out. Kilogram meter squared per second. So that's the angular momentum. 26 kilogram meter squared per second. Okay, now let's talk about rigid body dynamics. Up to now we've been discussing particle dynamics. Let me see what we're doing on time. Okay, resuming our discussion of rigid body dynamics, it might be appropriate to talk about what's a particle and what's a rigid body. And you probably feel silly if I ask you to hold up your hands in a room watching a television set, but you know, everybody that thinks a 747 aircraft is a let's talk about whether it's a rigid body or a particle. If you believe it's a rigid body, you know, hold up your hand and look silly like everybody else. Well, in fact, that's a trick question, because a 747 aircraft might be a particle or it might be a rigid body depending on the motion that it's undergoing. If it's undergoing pure translation, then the equations of particle dynamics apply to something the size of a 747. And I could ask you another trick question about you know, a billiard ball or a BB shot. Is it a particle or a rigid body? If it's undergoing pure translation, then you can apply the equations of particle mechanics. If it strikes a surface in such a way that it causes rotation, no matter how small it is, you have to treat it like a rigid body and apply the equations of rigid body dynamics. So the equations of rigid body dynamics now are distinguished from particle dynamics in this way. We put a subscript on the acceleration vector. Summation of the forces is equal to the mass of the rigid body times the acceleration of a certain point. Okay? G, we denote it, where G denotes the mass center of the rigid body. Not every point in the rigid body has the same acceleration. Now, if it's a 747 aircraft in pure translation, not undergoing any rotation, then every point has the same acceleration. And therefore, every point has the acceleration of the mass center. So you can forget that, and you can write summation of forces as mass times acceleration. And alpha is 0 when we get to that, in that case, and then it's a statics equation in the moments. So think about the problem and determine for your own purposes whether you need to apply rigid body equations or particle equations. The other equation that has to be applied is the angular equation for Newton's second law, which says that the summation of moments about point G, and the subscripts are pretty important here. We need to emphasize the importance of these subscripts where they appear. The summation of moments about point G is equal to I, the mass moment of inertia about point G, times the angular acceleration alpha. Now, the angular acceleration of the whole rigid body is the same at every point, so we don't have to have a subscript there. The 747, of course, you know, his wings are going to be bouncing around and it's going to be moving, so it's not a rigid body. If there's any deflection involved in it, then it's not a rigid body. It might be a flexible body that's undergoing pure translation. But only for that reason, if it's in pure translation, would the acceleration of, say, the wingtip be different than the acceleration of a point at the mass center? Okay. You either need to write these two equations, the summation of forces is mass times acceleration of the mass center, plus the summation of moments about the mass center is I about the mass center times alpha, or alternatively to this one, and sometimes advantageously, you can write, in certain cases, okay, the summation of moments about some point, point O, is equal to I about that point, point O, times alpha, where point O is some pinned point which has no acceleration. So if you have an object that's hinged about a certain point, it's sometimes to your advantage to write the summation of moments about that point and calculate the angular, the moment of inertia, mass moment of inertia about that point to calculate the angular acceleration of the body. But it's got to be a pinned point or certain other special circumstances. Best to remember that if it's not a pinned point, then you ought to always use a point G. What is the mass moment of inertia? It's a measure of the angular mass of the object in question. The definition is the integral over the volume of r squared, and this is measured from the point in question to the elemental mass dm over the whole volume. It's going to have units then of length squared times mass. Another way to write it is to say dm is rho, the mass density, times d volume over the volume. The best way to calculate it is to look at the handbook in the tables on page 28 to 29 in the NCEES handbook. M is the moment of all forces on the free body diagram about the point in question. That's either G, it can always be G, it can sometimes be some special point O in certain special cases, okay? But usually it's going to be, it's always valid about point G. And alpha is the angular acceleration. It's going to have units of 1 over second squared, or radians per second squared. Okay, an example of rigid body dynamics. Consider a thin disk, the specified radius 30 centimeters. Remember, that's not the proper unit in the SI system, so we're going to use meters. Mass 2 kilograms, that has a constant, doesn't vary with time, tangential force, doesn't vary with position, it's always tangential, of magnitude F is 10 newtons, that acts at an unknown moment arm R. So there's a lever out here somehow that's fixed to this disk, okay, that's massless. The lever's massless, the disk is not. And the force is applied to some point there. as the disc turns, the force always stays perpendicular to the arm, okay? It's called a follower force. Like if you had a thruster out there on the end of a satellite, it would always thrust in that particular direction and cause a force in that direction, regardless of the orientation of the satellite. We're asked to find the unknown arm at t equal 12 seconds. We're given the angular acceleration, 3t radians per second squared. Okay. At t equals 12 seconds, we evaluate alpha, and we find alpha is 36 radians per second squared. We write the equation for angular motions, Newton's second law. Summation of moments about point G. Point G, the mass center of the disk, is at its geometric center, is equal to I about G alpha. From the tables in your handbook, you find that and maybe this is something I ought to point to in the tables. The mass moment of inertia because it doesn't look like a thin disk. But this cylinder here, if h is very short, this is on page 28, if h is very short, the mass moment of inertia is about the y-axis, which is vertical, is Iy about c, they call it c, what I call g, is Iy is 1/2 mr squared, okay, where r is the radius of the cylinder. So that's the expression I took from this book here. And you notice that Iyc doesn't depend on h. So a thin disk and a cylinder of finite height h have the same Iy. Okay, now the other products of inertia and moments of inertia depend on h, but for a thin disk about its axis, the moment of inertia doesn't depend on h. So that is the moment of inertia I'm using in this solution. 1/2 mr squared, where r is this radius, and m is the mass of the disk. The moment about G, this is G, is r cross f, or in this case, they being perpendicular, it's r times f. And this is in this direction, okay? So alpha is going to be in that direction. Alpha is known. It's 36. So if I solve for r, okay, by dividing this, putting the f over here, I get 2 kilograms, which is the mass, times the radius, 0.3 meters squared, over 2, times alpha, I didn't have room to write alpha out there, times 36, that's 36, the decimal goes there, this is a multiplication sign, 36 radians per second squared, divided by the force, 10 newtons, I get the position, the radius arm, r, at that instant is 0.324 meters. And that's answer number A in the book by Lindbergh. Another example. Problem 13 on page 16-7 in Lindbergh. We're given a uniform rod. It's pinned at point C. Has length L. Point C is at the 1/4 point, L over 4 from end B. String OA is cut, okay, and that causes the bar to rotate. End A is going to fall, of course. We're asked to compute the acceleration of point B. I'm going to use the fact that C is pinned, and I'm going to write the summation of forces, a summation of moments about point C is I about C alpha. This is going to be advantageous to me because if I wrote the summation of moments about point G, I would introduce unknown forces at C, the unknown reaction Ry and Rx. I'd have 2 more unknowns. I'd have to write 2 more equations to solve for those unknowns. Those 2 equations would be the summation of forces is equal to mass times acceleration of point G. But if I write summation of moments about C is equal to I about C alpha, as opposed to using point G, I don't introduce these two unknown forces. I get a simple equation with one unknown alpha. So that's simpler. Mathematically, we say that this equation is uncoupled from the equation for summation forces equal mass times acceleration. It doesn't have the other acceleration terms in it or these other forces. So this equation can be solved independently. That's why it's convenient to use point C, and that's why I'm doing it. But I can only do it because point C has zero acceleration. It's pinned. Okay? I need to be able to calculate then I about C, and I've indicated here that you might have to review the parallel axis theorem to remember how to do that. The parallel axis theorem says that the moment of inertia about a point C is always found by adding to the moment of inertia about G a term d squared m. That's got the right units, length squared times mass. And d is the distance between C and G. Okay? Or it's the distance between two parallel axes through C and G. In this case, it's just the distance. It's L over 4 in the case of our problem. So, again, I look up the mass moment of inertia for a slender rod in the book, and that's in the tables here somewhere. Okay. Oops. This is a slender rod. Okay. I'm interested in the moment of inertia about, say, the y-axis, which happens to be the same as the z-axis, about point C, through point C, which is point G, right? Which is 1/12 mass times length squared. Notice this value right down here is about the end of the bar, 1/3 ml squared. Notice that's 4 times as big as that. The mass moment of inertia about any other point besides G is always going to be bigger than the mass moment of inertia about G. The mass moment of inertia about G is that's the point that the object has the smallest mass moment of inertia about. So I'm always adding something to I about G to get I about some other point. I'm adding a positive number, d squared m. So I about C is 1/12 ml squared from the handbook plus the mass m times the distance L over 4 squared, which gives me 7 ml squared over 48 for I about C. Okay? Now what's the moment about C? About C, I'm sorry, this is C. The only force that has a moment about C on my free body diagram, this is a free body diagram. The only force that has a moment about C is W. And it has a moment arm of L over 4. W times L over 4 is the moment about C. That's in this direction, so I expect alpha is going to be in that direction also. And of course, that makes sense. It's going to rotate in the counterclockwise direction as viewed from this side of the paper. So alpha is, solving this equation, alpha is m about C over I sub C. WL is mgl over 4 over I about C. 7 ml squared over 48 is 12g over 7l. Let's see what the units are here. This is length over time squared over length. So this is 1 over time squared. If I'm using SI units, it's going to be, well, no matter what units I'm using, it's going to be 1 over second squared, right? Radians per second squared. The right units for alpha. Okay, that's not exactly what they wanted me to find. They wanted me to find the acceleration of B, and we have to use some kinematics to do that. By kinematics, if we know the acceleration of point B, we can write the acceleration of point B as the acceleration of point C plus the acceleration of B with respect to C, alpha cross R B with respect to C, plus omega cross R. This is not in the handbook. The two-dimensional scalar expression, and let's see if we understand this, says acceleration of point B, since point C is pinned, is alpha, the angular acceleration of the link, times L over 4, the distance from B to C, or C to B, if you will. So the acceleration of B is L over 4 times alpha, which is 3g over 7. Answer number C in the table. Which way is it going to be accelerating? It's going to be accelerating upward, right? Which way is this going to be accelerating? What do we call that point? Point A. Point A is going to be accelerating downward. Point G is going to be accelerating downward. Okay? Initially, when it's at rest, when the string is cut. Okay, there are some other techniques that are useful. We've seen several examples of how you write and solve Newton's second laws, but there are a couple of other techniques that are very helpful in certain problems. And those are work energy and impulse momentum. The clue that's helpful, that's supposed to trigger in your mind when you use those approaches, is when you're asked for a final velocity. Now, when they ask you for the acceleration, that's a clue that they want you to write Newton's second law and solve for the acceleration of point B, like we did in the last problem. But if they had asked for the velocity after the bar falls, say, 45 degrees or something, they're giving us a clue that we want to use one of these two techniques. Okay? We could solve for the velocity of the bar after it falls 45 degrees in that last problem by calculating acceleration as a function of position, by integrating it, and it would be complicated, but we'd come up with the final condition of the bar. But there's shorter ways to do it, and these are very useful when you need to know the final conditions, the final velocities in particular. Let's talk about work energy and the work energy method. The work energy method says that the work, U12, is the kinetic energy at time or position 2 minus the kinetic energy at time or position 1. It says that for a system, say a rigid body free body diagram, the work done on the system, which is work U from 1 to 2, and I emphasize that by underlining it, the work done on the system, this is the word that really wants to be emphasized, as opposed to the work done by the system. This is the work done by the forces that act on the system. Between configuration 1 and configuration 2, or time 1 and time 2, or position 1 and position 2, we call that U12, equals the change in kinetic energy. The final kinetic energy minus the initial kinetic energy. If it starts from rest, this one's 0. If it winds up at rest, this one's 0, and that one's usually non-zero. So very often we will know one of those to be 0. Not always, of course. The kinetic energy of a rigid body is 1/2 the mass times the velocity of the mass center of the rigid body, g squared, plus, and that's the translational kinetic energy, plus the rotational kinetic energy, 1/2 I about g omega squared. I don't have to put a g on omega because every point has the same angular velocity in a rigid body. Now, in the special case of a particle, if this 747 doesn't have omega, you see, the kinetic energy is 1/2 mv. We don't have to write g because every point has the same velocity in the particle. It doesn't have any angular rotation. Whether it's a big particle like a 747 or a billiard ball. Potential energy is a concept that comes up sometimes in these work energy methods. In some cases, work can be computed very easily by the change in a potential energy. In the case of gravity, the potential energy due to a weight in a gravitational field is W times H, or mgh, where H is the height above some reference plane, reference datum, and that's the potential energy with respect to that datum of that weight in a gravitational field. Or, in the case of an elastic spring with spring constant K, the potential energy is K times x squared over 2, 1/2 kx squared. And it doesn't matter whether x is elongation or the compression of the spring, because it's squared. X can be positive or negative. The potential energy here is only going to be positive. if the spring starts from rest, from an unstretched position, and you compress it, shortening it, or stretch it, elongating it, you're going to store positive energy in that spring. It's impossible to get energy out of the spring if it's uncompressed. Now, if you start from an uncompressed position, if it's already compressed, then you have some potential energy. The change in potential energy from that compressed position could be positive or negative, depending on which way you change the elongation. But usually this is measured from the unstretched position. Okay, in terms of those two expressions for potential energy, the work done, U from 1 to 2, in a gravitational field is W times H2 minus W times H1, or W times H2 minus H1. Notice that if the mass goes down, H1's littler than, if it goes, let's say if it goes up, H2 is bigger than H1, okay, then this is a positive number. So if the mass is moved up in a gravitational field, the work done is positive. That's the work done by some force acting on the mass. Okay, the work on a spring is 1/2 kx squared at position 2 minus 1/2 kx squared in position 1. So if the spring is initially unstretched, x1 would be 0, and the work would be 1/2 kx2 squared. You can also calculate work by integral of f dot dr, integral of force times distance, or just if it's a constant force, force times the distance, and that's positive or negative depending on whether the force is in the same direction as the displacement, as the travel, or in the opposite direction. Let's see, a couple more points that I want to make about energy. In the special case when there is no work done on a system except by changes in such potentials, the work done on a system is equal to the change in potential energy. If there's no other work done except by changes in potential, then the work done is equal to the change in potential energy. And the work between 1 and 2 is equal to the change in kinetic energy, so we have the result that the change in potential energy equals the change in kinetic energy, or the potential energy at time 2 we took a pause there. I've discovered a minus sign missing from my notes here, so I'm going to correct this page and the previous one. We're going to have a minus sign here, okay, which will make this equation compute. And on the previous page, I'm going to put a minus sign right here, okay, minus sign, here and here, okay, and here. So when we're calculating the work done, it's equal to the negative of the change. It's the negative of the change in potential. Let's see if this makes sense now. The work done on a mass that moves downward, when it moves downward, H2 is littler than H1, so this is negative, and the minus sign makes it positive, so the work done by gravity is positive. Okay? The work done by the spring, I think you can convince yourself likewise we need a minus sign in front of there. I apologize for the error. Now the minus sign should be fixed here, and when we put that minus sign in there, the negative of the change in potential energy, we get this result, which is sometimes referred to as conservation of mechanical energy. Now it doesn't always hold. Don't say that mechanical energy is always conserved. This is only in certain cases. Remember, when no work is done on a system except by changes in potential. If you have, for example, friction, you can't develop a potential that describes friction. It mathematically can't be done. So in case of friction and some other forces like that, mechanical energy is not conserved. But let's see what mechanical energy, what conservation of mechanical energy says. When it applies, it says that the potential energy plus the kinetic energy at time 2 is equal to the potential energy plus the kinetic energy at time 1. Is that what it says? Plus kinetic energy, potential energy, kinetic energy time 1 minus, yeah, okay? Okay, and an example of the application of work and energy is this same problem. Now, the problem's in the book earlier when they asked me to find acceleration of this point here, but this particular problem is not in the book. I'm going to use the same geometry as an example of how to use work energy to find the final conditions of a rigid body problem like this. Given the pin beam that falls 45 degrees, what's the angular velocity omega at that time? And it starts from rest. So that string is cut, it's at rest, it falls 45 degrees, and we're trying to find omega for the beam. The hint here that you're supposed to see is that the problem asks us to find the final velocity. Here it's an angular velocity. Okay? That hint tells you that work energies are going to be a useful tool to you. Okay, solution. Let's look at the beam at 45 degrees. At the angle of 45 degrees, the beam has fallen. The beam's center, mass center G, has fallen how far? Well, L over 4 is this distance, okay? L over 4, and it's fallen L over 4 times the sine of 45 degrees, or L over 4 square roots of 2. The work done by gravity is then U1 to 2 is W times L over 4 square roots of 2. It goes down, so gravity does positive work, so this work is positive. So the gravity does that much work. Work energy theorem, or principle, says that the work between configuration 1, when it's at rest, and configuration 2 is equal to the change in kinetic energy between those two times or conditions. But it starts from rest, so kinetic energy 1 is 0. So U from 1 to 2 is 1/2 the mass times the velocity of point G squared plus 1/2 I about G omega squared. That's the definition of the kinetic energy at time 2. I haven't put a subscript 2 on omega and a subscript 2 here because there's only one time in question. We're not concerned about time 1, we're concerned about time 2. These refer to time sub 2. Okay? We can relate by kinematics the velocity of the mass center and the angular velocity. V sub G is L over 4, the distance from the pin to the mass center, times omega. Therefore, I can substitute for V sub G, L over 4 omega, and I write down U12, which is WL over 4 square roots of 2. This has units of work, of course. Force times distance. Is equal to 1/2 the mass times V sub G, L over 4 omega squared, plus 1/2 I about G, ml squared over 12, we looked that up earlier, times omega squared. Or MGL, WL, MGL over 4 square roots of 2, that's the work. On the right side we have mass times length squared times omega squared over 2 times 1/16 plus 1/12, or omega squared is 7 over 96 square roots of 2 times G over L. Square root of that is omega. What are the units? The units of G over L are 1 over seconds squared. So the units of omega are 1 over seconds. Okay? Which are the proper units for omega. Now there's really an easier way to do this. It turns out that if we had known that the kinetic energy could also be expressed as 1/2 I about C times omega squared, where point C is a pinned point. This is not in the handbook. But if you can compute I about C, then you uncouple the equation. You don't have to write, you can write the kinetic energy without using V sub G. It's 1/2 I about C times omega squared. And you can solve that for the same result in a little bit shorter step because you don't have that kinematic relationship between Vg and omega. So it's a little easier. But you get the same result for omega. What do? We calculated the work. Which is work due to gravity. It's positive. It has magnitude weight, or mgl, over a number. Because the work is positive, the kinetic energy is going to increase from 0 when it starts out to some final value. And the final value, we know from the definition of kinetic energy, we can write it in terms of omega. Here it's in terms of Vg and omega. We relate Vg to omega by kinematics, and we get an equation in omega and known work that we can solve. So work energy is very fast. We didn't have to write and integrate equations of motion. We didn't have to calculate accelerations at every time. We simply looked at the difference in potential energy, if you will, because that's the work done, between initial time and the final time, 45 degrees later. We set that equal to the change in kinetic energy, and we came up with a very easy solution for the kinetic energy at time 2, and therefore the speed at time 2, the angular velocity. Let's look at another example where work energy is helpful. Let's say you're driving your new pickup truck down the street, and the front wheel comes off. So we've got a disk of mass m that comes off a vehicle that's traveling with speed v0 on a horizontal plane. And the question is, if there's a hill there, how high will a wheel roll up the incline? The 1% is a red herring. It doesn't matter, it turns out, but if you're given the incline, you might think you need to know the incline to solve for the height that's going to roll up. The statement of work energy says that the work between time 1 and time 2 is a kinetic energy at time 2 minus kinetic energy at time 1. Well, when the disk is as high up the plane as it's going to go, it comes to rest. We're going to assume it rolls without slip, and so when it stops for an instant, it has 0 velocity and it has 0 angular velocity, and so the kinetic energy at point 2 is 0. Now it might be that if it's bouncing up the hill, okay, and it hitting pebbles along the way or irregularities in the road, it's going to be bouncing, and maybe at its highest point it still might have a little angular velocity. But we're assuming here it rolls without slip, which is a kinematic simplification. So the kinetic energy at the top is 0. The kinetic energy at the initial time down here is 1/2 the mass of the disk times the initial velocity of the mass center, which is v0, the same as the truck, plus 1/2 the moment of inertia of the disk about its own mass center times omega squared. By kinematics, we can relate omega and v0. Omega is v0 over r. And so we can compute the kinetic energy in terms of omega or v0 alone. Okay? The work done between those two times is equal to the weight of the wheel times the height up the incline that the wheel is going to roll, the vertical distance. It's negative because it's going uphill. The work tends to reduce the kinetic energy. H is a positive height, so we've got to have a minus sign. So the work minus WH is equal to minus kinetic energy at time 1. KE2 is 0. I haven't written that, but that's KE2 minus KE1. So minus kinetic energy at time 1, 1/2 mv squared plus 1/2 moment of inertia about g times v0 squared over r squared. The minus sign on both sides goes away. Mgh is 1/2 mv0 squared plus 1/2 I about G is mr squared over 2 times V naught over R, all squared. MGH is 1/2 M times V naught squared plus this boils down to V naught squared over 2. Let me think about that one. V naught, yeah, here's my 2, okay. The 1/2 comes out, there's my 2, okay. R, MGH is 3/4 M V naught squared. H is then 3/4 V naught squared over G. It's got units of meters per second squared, that's V naught, over meters per second squared, that's G, or meters, which is the proper units for height. Okay. So that's the height that wheel is going to go up the plane. In review, we were given a disk with initial conditions of speed and angular velocity, assuming it rolls without slip, and from that we can compute the kinetic energy. Knowing that it's rolling uphill against a gravitational potential, we can determine by work energy the height, the distance it has to go uphill before that kinetic energy is all converted to potential energy, and it comes to rest. Of course, then it starts back downhill. One point I want to make is that particular object, you notice, had significant kinetic energy due to translational, 1/2 mv squared, and rotational terms, 1/2 I omega squared. And it's a lot of energy. When a tire gets loose on the highway, it does a lot of damage. That's a measure of how much energy is in that tire. Let's look at the rest of the problem and see what we can learn from it. Let's assume that once the wheel comes off the car, the chassis hits the ground, and there's a known friction force F. You know, you might say it's some fraction of normal force, mu n, but the point is, let's just assume we know the friction force F, and we're asked, can we determine how far the car will skid before it all comes to rest, given that the weight of the total weight is the weight of the car, some without wheels, plus 3 wheels, right? Because we lost one. And I'm doing this to show you that sometimes the kinetic energy of the rigid, it's not just a rigid body, it's a system now of a rigid body, the car, and 3 other rigid bodies that are rotating. So the total kinetic energy is what's going to be interesting to us here, how we calculate that. The final kinetic energy, again, is 0. Now this time T2 refers to the time when the car comes to rest, not when the wheel comes to rest up the hill, but when the car comes to rest. Work from 1 to 2 is the work done by friction. That's the only thing doing work on this car. And it brings the whole thing to rest. So the kinetic energy at time 2 is 0, and the kinetic energy at time 1 is what we have to compute. The kinetic energy at time 1 is 1/2 the mass of the chassis without any wheels